As we explained in the first video of this section 6.4, the way to detect gravitational waves is via the deviation, the geodesic deviation they produce on free-falling particles. If you remember the formula of geodesic deviation, it depends on the curvature, on the Riemann curvature tensor, in fact, and okay, if we want to study this geodesic deviation, we have to start by computing the Riemann tensor associated to these waves. Well, remember that the metric that we are studying is this one, where now h mu nu is the h mu nu associated to a gravitational wave, which we take for simplicity of this form, and where epsilon mu nu, the polarization tensor, is restricted by gauge choices that we have made to be composed of these only 4 non-vanishing components, okay, and only 2 of them independent, epsilon plus and epsilon x. Okay, so well, let's start by computing the Riemann tensor. This is something that we did in lecture 4 when we studied the weak field limit of general relativity, because in order to find the weak field expansion of the Einstein tensor, we first had to compute the weak field limit of the Riemann tensor, and there we found that R mu nu rho sigma was of first order in kappa, and then is given by partial rho and this antisymmetrized derivative minus partial sigma mu, and this also antisymmetrized. Now you just have to plug the solution into this formula and take the corresponding derivatives to find the Riemann tensor. Remember that epsilon is constant, so you only get derivatives of sine of kx, and that the partial mu of sine kx is just k mu cosine kx. Okay, then what you get is chi. There will be an overall factor of cosine kx. Well, you take 2 derivatives each time, so it will be minus sine, then there is k rho, k mu, and epsilon rho nu, minus k sigma, k mu epsilon nu rho, and everything multiplied by sine kx. Okay, so this we have. Now let's go to the geodesic deviation equation. Remember that we managed to write it in this form. Okay, but this xi was the deviation vector, and you get R mu nu rho sigma, and there are 2 vectors u contracted with the indices. It cannot be with mu and nu because it is antisymmetric, so one is with mu. The other one will have to be contracted with rho, and the other vector is a deviation vector nu, sorry. Okay, now in order to simplify a bit more the calculation, we are going to work also in a freely falling coordinate system, which means the following, that first this will be given by just the second derivative with respect to s of psi sigma, and because remember that in this free falling system you just can set to 0 this the connection, so these covariant derivatives become just ordinary derivatives. And the second thing that happens in this freely falling system is that u mu only has a zero component. Okay, so it's just delta mu 0. So if we have to compute products of u mu and k with the choice of k that we have made, this is just omega, which was the zero component of k. Okay, kind of written like this. This would be k0, and this is just omega if we have to write it. Okay, so this means that the components that are relevant here will be 0, 0, and sigma and psi nu. So the formula reduces to this. And furthermore, if the particles are moving slowly, this deviation vector will be such that psi 0 can be taken as approximately 0. Okay. And only the components psi I are different from 0. So the only equations we have to worry about, okay, observe that the 0 component of this equation, so when sigma is 0, is automatically satisfied in this approximation, because you get 0 nu, only I, 0, and this is 0, and this is because of the antisymmetry of the Riemann tensor in this pair of indices, or this pair of indices, but in this one here, this is identically 0. So this is satisfied, and we only have to worry about the spatial components. So the equation simplifies, and we just have to study this equation. Approximately R0 J0I, okay, and psi J. But we just computed what R0 J0I is. We just have to come here, okay, and we see that this is minus chi. Okay, let's see here rho. First I write the whole equation, and then I set the values of the indices. I think it is more difficult to make mistakes this way. Okay, and this is multiplied by sine kx, and this will be contracted with the second index. The second index here is nu, so nu will become j, and this comes multiplied by psi j. Then the index mu is 0, and also the index rho, which is the third here, is 0. Okay, I think, yeah, I made a mistake here. This is sigma, sorry. Okay. So if rho is 0, this is also 0. And here we also have 0. And finally, sigma, which is here, is I and I. So this is what the equation reduces to. In this term, there are two terms because of the antisymmetrizer. So one of them is k0 epsilon j0, which is 0 because of our choice that the mixed space-time components of the polarization tensor vanish, and the other term will be kj epsilon 0 0, epsilon 0 0, which also vanishes because of the choices we made. So this term vanishes, and in this one, only you have epsilon ij, and k0. So k0 epsilon ij is okay, but only certain components will be different from 0. And kj epsilon 0 is 0. We can remove the antisymmetrizer and just leave this here and with a factor of 1/2. Okay, and this will be the non-vanishing component. So if I write this to get a cleaner equation, this is minus chi over 2, then k0, but k0 is omega, so this is omega squared, epsilon ij psi j sine kx. This is almost the equation that we are going to solve in the end. We just have to express it in terms of the coordinate time. First of all, this s is going to be c times t because of the slow motion that we have assumed. And kx is k0, the only non-vanishing component, which is omega divided by c times x0, and the other component, which is different from 0, is k3, which is also omega c, so multiplies now minus x3. Okay, since x0 is c times t, this is omega t. If I take omega common factor, this is minus x3 divided by c. So, in conclusion, the equation becomes d squared psi I dt squared, and okay, approximately or equal, let's write equal. You know that we are working with certain approximations. Then c comes here multiplying, and we have epsilon ij psi j and the sine of omega t minus x3 divided by c. Okay, this is the equation that we want to solve. The solution, expressed as an expansion in chi, we are working in this weak field approximation, is just psi of t is psi of 0, some initial value of the deviation, plus chi over 2 psi j evaluated at 0, epsilon ji, which is constant, then this sine of omega t minus x3 divided by c, plus terms of higher order in chi squared. And this can be checked by substituting this in the above equation and ignoring terms of second order in chi, like the ones that would come from replacing here this psi j by of 0 by the full psi j. These are of higher orders. So this is why this solution works, because here replacing the full psi I with this term generates a term of second order in chi that you ignore, and this is why only psi j of 0 remains. Now, well, because of the choices we have made, that you see that epsilon ji only has non-trivial components in the directions 1 and 2. So if the index I or j is 3, nothing happens because epsilon vanishes, and epsilon 3, for instance, psi 3 of t is just psi 3 of 0. There is no deviation in the third direction to second order in chi, of course. So we have to study just psi 1 and psi 2. This we are going to call x and y. okay, but they are just deviations, and we are going to rewrite these equations in this simpler looking way. We have this component chi over 2. If epsilon, if this index I is 1, then j is either 1, okay, and then you have x0, and you have epsilon 1 1, which is epsilon plus, or you have 1 2, and then this is epsilon x, and then you have y0. Okay, and there is a sign which should be plus if this is the same sign that you get here, and sine omega t minus x3 divided by c. And here this will psi 2 of 0 we call y0, and then there is chi over 2. And again, if this is 2, well, when j is 1, this is x0. But this is 2, 1, this is epsilon x. And then when I is 2, then and j is 2, this is minus epsilon plus, and this is y0. This is minus y0 epsilon plus, and with the sign. Okay, so these are the two equations that tell you what are the deviations in the directions x and y. Now we rewrite these equations. We take here x0 as a common factor. So we write 1 plus chi over 2 epsilon plus, and sine, I just write sine. It is understood that this is going to be the sine of omega blah 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 times x0 plus epsilon x chi over 2, and this sine and everything multiplied by y0. We do the same with y. Here we take this as common factor. It is 1 minus chi over 2 epsilon plus, and this sine y0 plus, and epsilon x chi over 2 is sine and x 0, always plus terms of order chi squared that we just don't consider. And then we are going to consider separately the cases in which epsilon x is 0, and then the case in which epsilon plus is 0. And epsilon x is 0, this corresponds to the polarization mode plus. Okay, so in this case you only have this term, because the second term vanishes, so it is 1 plus sine x0, and y of t equal to 1 minus chi over 2 epsilon plus sine and y0. And now, if you divide this first equation by 1 plus chi over 2, etc., okay, you get, so we are in this case, so this is x of t divided by 1 plus chi over 2 epsilon plus, and this sign, this is x0. Do the same for y, or it's not the same, but an analogous thing for y. This is equal to y0. Then you square both sides of these two equations, and you sum these two equations, and the result is that x divided by 1 plus chi over 2 epsilon plus, and this sign squared plus y of t divided by 1 minus chi over 2 epsilon plus and sine of blah 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 squared is equal to x0 squared plus y0 squared. Okay, so let me keep this result and then we will interpret it, okay, or do something to visualize what this means. And now I will consider the case epsilon plus equal to 0. Okay, and in this case, if I look here, I get x of t is equal to x0 plus epsilon x chi over 2 sine y0, and y of t is y0 plus epsilon x chi over 2 this sine, sorry, this is 0 and this is x 0. This is the other possibility. In this case, what we want to do is to sum these two equations and also to take the sum and the difference. So we get in one case xt plus y of t, this is x0 plus y0 plus epsilon x chi over 2 this sine, and also x0 and y0 is a common factor, so we can write this in this way. Okay, if I take the difference, well, we get something very similar, x0 minus y0, but here it is a minus. Okay, if I am not wrong, because you want to take, you're going to subtract this one, so this comes with a minus. Okay, and now that I have these two equations, I do the same as I did before, but for these two combinations, I divide by this whole thing, so I get xt plus yt divided by 1 plus epsilon x chi 2 on this sine. This is equal to x0 plus y0. There are equations that don't want to be written, so they run. Okay, this is 1 minus epsilon x chi over 2 and this sine, and this is equal to x0 minus y0. We do the same as before. Okay, so if we used instead of the coordinates x and y a new coordinate which is the sum and another coordinate which is the difference, these equations and these equations would be exactly the same. Now we sum, and we have x of t plus y of t divided by 1 plus epsilon x chi over 2 on this sine squared plus x of t minus y of t divided by 1 minus epsilon x chi divided by 2 and this sine squared. This is equal to x0 plus y0 squared plus y0 x0, sorry, minus y0 squared, and this is the second equation. You see that it's basically the same equation as before, but for another two coordinates. So instead of for x and y, which correspond to these two axes, it is for x plus y and x minus y. which correspond to these two axes. And this is why this polarization mode is denoted by this epsilon x, and the former polarization mode is denoted by epsilon plus. Now, what do we make of these equations? So suppose that instead of having an infinite number of particles, you just have a set of particles which are initially arranged in a circle that you can take as a circle of radius 1. So initially you have this equation. So you only consider those particles that satisfy this initial condition. And then if you consider this, impose this condition, this initial condition in this equation here, what you see is that in one case you have, maybe I should try to copy this equation instead of writing it completely. So here it is, this is equal to 1. Okay, so this is for epsilon x equal to 0. And then for epsilon plus equal to 0, if we impose this condition here in the second equation, we get this, which by the way, you can simplify this and you get 2 times x0 squared plus y0 squared. Okay, and what you get is this equal to 2. So what is this? At any given instant of time, so sine takes some given value, what you get is that the points where these particles are, which are these x of t, okay, we are not just considering one, but we are considering a set which were arranged in a circle. Now they satisfy a slightly different equation. It's not just x squared plus y squared equal to 0, but x divided by something plus y divided by something equal to 1. This is an ellipse. And the same for this. So these are two ellipses. And the question is how these two ellipses change with time. This is something that you can easily emulate with a computer. Okay. In each case, the thing that changes are these two values. Okay. So these will be ellipses whose shape changes with time. At t equals 0, it's a circle. Okay, so it is this circle. Then at different times, time equals 0, this vanishes. If we set the initial conditions right, this will also vanish, and you have 1, and you have this circle. And this makes me realize that probably you need to say that x3 is 0 for t equals 0. But then at a later time, then this sign will increase. Okay, so this will increase and this will decrease, and this takes place in the x and y direction. So in one case, well, you start with a circle, time passes by, and then this becomes more like this shape, okay, up to a point. Then this this comes back to the circle, but then it starts stretching in this direction, okay, from more round to more elliptic, more eccentric, if you want. And here the phenomenon is exactly the same. Okay, the fact that you have a 2 is irrelevant. Qualitative. We just want to study this qualitatively, and the phenomenon is exactly the same. You start with a circle, but now the ellipses form in this direction and also in this direction. And this is something that happens periodically. Okay? You start with a circle, this circle starts stretching for instance, in this direction, then comes back, and then it is in the other direction. If you just think a bit on this and you interpret this constant correctly, okay, as the semi-axis of these ellipses, then you arrive to this. To illustrate this a bit better than with my drawings, I'm going to show you a computer simulation of the effect of a polarized gravitational wave on free-falling particles arranged in a circle. Okay, this is what comes next. To this. Now this gives you an idea if these are of how to detect a wave which is polarized in this way, because this is what happens to particles. Okay, you have free falling particles and you observe them in this way. Well, if you can measure this stretching in these two directions, then you detect the gravitational wave. This is basically what these detectors do. They are these interferometers. Okay, basically Michelson-Morley interferometers in which they send a ray of light in this direction, which is split by a semi-transparent mirror here, and it comes in this direction, and then rejoin again, and they interfere here, and the interference is measured here. So if this arm stretches or gets longer, okay, it will do, and it coincides with this polarization also, but that this corresponds to these two axes. This will become shorter when this becomes larger. Okay, and this is in this way the detection is maximized because the interference pattern will be more noticeable. Okay, if the polarization mode coincides with this, then it is this still you will see an effect. So this is probably the design which is optimal, but of course it prefers certain kinds of polarization. Nevertheless, the waves that you will detect are not do not have to be polarized. Okay, they will be composed of elementary waves with their elementary polarizations, but it will be a superposition of them, and you will detect at least those which are polarized in this way in some in a larger amount than those which are polarized in a different way. Studying exactly how this comes about would take much longer. I think there are references if you want to read in the program. The way to measure distances and times is really to send light rays. It's very difficult to measure a distance in any other way. If you put a ruler here, this ruler will also be stretched or contracted in exactly the same way as the detector, so that's not the way to do it. Also, this is a space-time effect. Okay, so time also will be affected in some way. So the way to do it is really with light rays. That's the only way to do it if you want light rays or any other electromagnetic radiation. To conclude this video and also to illustrate how detectors work, just the basics that I have told you about, I'm going to show you the video that LIGO prepared after the first detection of a gravitational wave associated to the merging of two black holes. This is what comes next.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our Sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.